Welcome to this explainer. Whenever we gaze up at the night sky, it's easy to assume this perfectly ordered cosmic machinery was just always there. But the actual story? It is a fascinating multi-million-year detective story where a chaotic, swirling cloud of dust somehow became the solid world we're standing on today.
It's the ultimate mystery of our existence, really. Where did the Earth come from? To solve it, we have to rewind the clock way, way back. We're talking about an era long before any human, dinosaur, or even a single-celled organism was around to see it. We basically have to play cosmic detective, piecing together clues left behind in meteorites, the orbits of the planets, and deep within the Earth itself to make sense of this massive puzzle.
This absolute behemoth of a cosmic construction project started exactly 4.6 billion years ago. To put that enormous number into perspective, all of recorded human history is just a microscopic blink-and-you-miss-it blip at the very end of this timeline. Back then, there was no blue marble, no oceans, not a single breath of air, just an unimaginably vast, freezing cold, slow-moving cloud of interstellar material floating out there in the Milky Way.
So here is our exact blueprint for building a solar system from scratch. Number 1. The solar nebula. 2. Dust to planetesimals. 3. Planetary embryos. 4. Giant cosmic collisions. And finally, number 5. Forging the Earth.
Let's jump right into Section 1, the solar nebula and the raw ingredients of space.
The leading scientific model for this is called the nebular hypothesis. And what's absolutely wild about this concept is the sheer scale of it all. Our original proto-solar cloud was about a full light-year wide, and the recipe was actually super simple. It was packed mostly with hydrogen and helium, just the basic primitive elements left over from the Big Bang billions of years prior. Only about 2% of this massive cloud contained the heavier chemical elements we recognize today.
But here's the thing. Clouds of gas in space can just sit there, doing absolutely nothing, indefinitely. Something dramatic had to happen. Scientists believe a massive external force gave it a nudge, maybe a shockwave from a nearby exploding star, a supernova. Or perhaps the cloud passed through a dense spiral arm of the Milky Way. Whatever the trigger was, it caused the cloud to start collapsing under its own gravity. As all that material was pulled inward, the cloud began to spin faster and faster to conserve its angular momentum. Kind of like an ice skater pulling their arms in. Eventually, it spun out into a flattened, equatorial disk, with a blistering young proto-sun heating up right in the center.
Moving right along to Section 2. Dust becomes planetesimals, basically how tiny grains transformed into massive rocks.
Researchers looking at the latest computer simulations and cosmochemical data usually break terrestrial planet formation down into 3 distinct phases. Step 1 is dust to planetesimals, Step 2 is planetesimals to embryos, and Step 3 is embryos to planets. We are zeroing in on Step 1 right now.
This phase actually features a really famous scientific puzzle called the meter-size barrier. See, when drifting dust clumps into centimeter-sized pebbles, gravity isn't quite strong enough to pull them together yet, so they just drift toward the central star. And at those speeds, when meter-sized boulders collide, logic dictates they should just smash into pieces, not stick together. So how on earth did they grow? Well, scientists now believe that graviturbulent forces, think of them like giant cosmic whirlpools in the disk, concentrated huge swarms of these tiny particles. Under their collective gravity, these swarms collapsed directly into much larger 100-kilometer planetesimals, completely bypassing that destructive meter-sized barrier. Pretty clever, right?
This whole process is perfectly mapped out in what scientists call the Safronov-Wetherill-Kallo scenario. I know, it's quite the mouthful, but it brilliantly illustrates how that early, flat disk of fine dust began to clump together, eventually forming an entire chaotic system of asteroid-sized intermediate bodies, which we call planetesimals. And it's from this swarm of rocks that the next stage of our solar system emerges.
Which brings us to Section 3, the era of planetary embryos, where the serious growth happens.
Once you've got a disk full of planetesimals, gravity completely takes the wheel, but it does so in 2 distinct phases. First up is runaway growth. This is where a few lucky bodies that are slightly larger use their stronger gravity to gobble up surrounding material exponentially faster than everything else. Their mass just rockets upward. But eventually their massive gravitational pull stirs up the smaller rocks so much that this runaway growth stalls out. That leads to Phase 2, oligarchic growth. This is where a small, exclusive group of surviving, massive planetary embryos slowly compete for whatever leftovers remain in the disk.
This entire growth engine is driven by a process called accretion, which is just the scientific way of saying bodies colliding and sticking together. And what's truly astonishing here is the speed. Through the raw power of accretion, planetary embryos, roughly the size of our Moon or Mars, formed in incredibly short timescales. We're talking just 100,000 to 1 million years. On a cosmic scale, that is literally the blink of an eye.
All right, let's get into Section 4, Giant Cosmic Collisions. Things get incredibly chaotic here. Up until now, the thick gas of the original solar nebula was acting like a giant cosmic cushion, damping the orbits of these massive embryos and keeping them relatively stable and circular. But eventually, the energetic solar winds from the young sun blew all that stabilizing gas out into deep space. Without that cushion, the gravitational interactions between the embryos made their orbits wildly unstable. They started crossing paths, playing a deadly, high-stakes game of cosmic bumper cars. This led to massive, hit-and-run collisions that shattered some bodies completely and merged others together.
So the real takeaway here is that this brutal elimination round, which lasted tens of millions of years, was absolutely essential. Out of a disk that started with dozens of massive planetary embryos, only 4 rocky terrestrial planets actually managed to survive the chaos to clear out their orbital neighborhoods: Mercury, Venus, Mars, and our very own Earth.
And that brings us perfectly to our final chapter, Section 5, Forging the Earth.
Building a planet like Earth is a violently transformative process. Those continuous, massive impacts generated so much heat that they literally melted the Earth's surface into a global, incredibly deep magma ocean. As the Earth grew under these extreme temperatures, heavy metals like iron separated from the silicate rock and sank all the way down to form the Earth's metallic core. At the exact same time, the heat caused volatile compounds inside the impacting rocks to vaporize, bubbling up to wrap this completely molten planet in a thick, primitive proto-atmosphere.
Let's just step back and look at this timeline for a second, because it really puts the unimaginably long, slow cook time required to bake a habitable world into perspective. We start at 0 with a freezing molecular cloud collapsing. Within just 100,000 years, a spinning disk forms. By 4 million years, the dust has completely bypassed the meter barrier to become massive planetesimals and embryos. But then it takes a full 30 to 100 million years of chaotic, violent impacts for the Earth to finally clear its orbit and finalize its rocky formation.
Honestly, thinking about all of that makes it hard to comprehend our planet today. When you look at that iconic blue marble, looking so peaceful and serene against the blackness of space, it's wild to think it was forged in such an exceptionally chaotic, hot, and violent sequence of events. Every single drop of water, every piece of rock around us, is a survivor of a 4.6 billion-year-old game of orbital pinball.
And that leaves us with a truly humbling thought to wrap up this explainer. You see, our solar system didn't just form and then hit the pause button. It is still a dynamic, moving, gravitationally interacting machine. Minor asteroid impacts still happen today. So if incredibly violent collisions were the primary architects that shaped our past, we are left to wonder what massive cosmic events might still be waiting out there to reshape our